Our speaker today is Dr. Rodney A. Brooks.
Not the Rodney A. Brooks. There's another one in robotics. I'm not him.
I was not going to say that. If you do you all should be using DuckDuckGo, of course. If you do a search for Rodney A. Brooks, the computer scientist will come up. And when I first made contact with him, I thought he was a computer scientist. Big surprise. He received his PhD in physics from Harvard in 1963. His mentor, his thesis advisor, was Norman Ramsey. After graduating from Harvard, he went with Transonics. He was a postdoc at Harvard for a couple of years, and then he went with Transonics for 8 or 9 years. And then he went to NIH and spent 25 years at NIH, published 124 peer-reviewed papers on medical imaging primarily. He retired from NIH in 1999. He and his wife had the experience of living in New Zealand for 9 years, which I envy, but mainly because of trout fishing. During his time at Harvard, as he's going to tell you, he attended the famous 3-year-long presentation about quantum field theory by Julian Schwinger, and that sort of stimulated some of this. This led him, from after his retirement from NIH, to write a book. Well, this is his copy of the book. I have a copy here. Fields of Color. It's a book written for the layman, not for us actually, about quantum field theory. At this point, here's the title of the talk, and I'm going to turn the stage over to Dr. Brooks.
Hey, thank you, and thank you very much for inviting me here. First, I want to tell you my story, why I'm here, why I wrote the book, and then I'll tell you what I know about quantum field theory. In 1956, I started graduate school at Harvard, and I had no idea that I was so fortunate to be in the right place at the right time. Julian Schwinger, how many people have never heard of Julian Schwinger? See, look at that. Julian Schwinger was one of the greatest physicists of all time, certainly one of the greatest of the 20th century. He perfected quantum field theory. In 1956, he had just finished his 5-part masterpiece, The Theory of Quantized Fields. He was presenting a 3-year cycle of courses at Harvard, and I walked into his class being completely ignorant about all of this, but began to learn quantum field theory, as it turned out, from the master. And I believe that anybody who didn't learn quantum field theory from Schwinger didn't learn quantum field theory. Anyway, you might have read this quote here, and it's very true. His lectures were masterpieces, conducted without notes, fluently, in perfect sentences, et cetera, et cetera, et cetera. But the flip side of the coin is that Schwinger was very hard to understand. And even for us students who sat there, week after week, 3 years, we would pore over our notes and try to make sense out of it. Freeman Dyson said once, Schwinger's lectures, this is referring to specific talks he gave after his 1948 success, Schwinger's lectures were almost incomprehensible. Freeman Dyson. J. Robert Oppenheimer, who was Schwinger's sponsor, said, other people, and I like this one, other people give talks to tell you how to do it, but Julian talks to tell you how only he can do it. Because his approach was very idiosyncratic and very hard to follow, and that's part of the tragedy of why Schwinger and quantum field theory are forgotten. Well, this was great, but then I had to go earn a living, and so I went, as Wes told you, I went into other fields, and when I retired in '99, I began to take up a project, and it eventually led to this book. And the reason is I began to see, as I looked around and read, and wherever I turned, magazines, whatever, I began to see that field theory had been forgotten. All you saw was particle physics. Particles, particles, particles. And mysteries and absurdities and paradoxes. I got hold of Feynman's book on quantum electrodynamics, and he says, leave your common sense behind you. But I thought, no, quantum field theory is full of common sense. So I came out, and it took me quite a while, and I wrote the book. But I want to tell you, and I want to make this clear, and I think you understand, I'm not an expert, and I never was an expert on quantum field theory. And if some of you want to ask me some like highly mathematical questions, I won't know. Anyway, that was so long ago that I've forgotten half of what I knew anyway. So I'm here to tell you the concepts, what I remember of this. Okay. I'm now going to tell you about, briefly, the history of the battle between particles and fields, as I explain it in my book, in the first chapter, actually. The way I see it, there were 3 rounds of the battle, and they're really quite interesting. The first battle occurred in 1905. Up until then, everybody was pretty content with electromagnetic fields, and the gravitational field was beginning to be accepted also as a field until Einstein's 1905 paper, where he showed that the electromagnetic field, well, let me just read a little bit of this. On the one hand, a single photon can interfere with, and I'll show you that in the next slide. It is evident that Maxwell's theory cannot account for this, yet the interpretation of the photon as a point-like structure does not admit of an explanation for the interference phenomenon. And a very poignant quote, 1951, 2 years before or 3 years before his death. All these 50 years of pondering have not brought me any closer to answering the question, what are light quanta? And I have a nice passage in my book of what might have happened if Schwinger had happened to go to visit Einstein in 1953 before he died, and it might have come out differently. The problem is illustrated here, and I know you're all familiar with the 2-slit experiment. And on the left, you see the diffraction pattern that you get from light passing through 2 slits. Fine, it's a field. But if you turn down the intensity of the light and you get 1 photon at a time going through, each photon interacts with one specific atom in the detector. And you get a dot here and a dot there. It sure looks like a particle. Now, to jump ahead, just to tell you what's coming a little later, what we're seeing here, according to field theory, according to quantum field theory, is called field collapse. Yes, and I mentioned Art Hobson before in his article. Art Hobson thinks that this picture, this diffraction pattern alone, is overwhelming evidence that forces you to understand and recognize that a photon is a spread out field. It has to be. How else can you get that pattern? And it collapses and deposits all its energy, suddenly violating locality. Violating the locality principle. Okay, I'm rambling on. So that's round 1. And the picture on the right, you know, the particle properties of the photon eventually push people in the direction of particles. Round 2 came around the 1925 or so, and quantum mechanics was developed. Schrödinger, de Broglie introduced the idea that the electron is a wave. Schrödinger came up with a wave equation, and he wanted to believe that there is indeed a field. Just like the electromagnetic field, the electron is a field. But he also, for the electron, he looks at a picture of the cloud chamber as the electron goes through, and how can you not believe that's a particle? How can you believe anything but that it's a particle? It sure looks like a particle. Jumping ahead, again, the answer is a series of interactions as the electron field collapses into one atom of the detector, of the cloud chamber, and then propagates and then interacts with another and another. But still in all, Schrödinger did not win that battle. He sort of gave up himself. We find it confoundedly difficult to see this as fields. And round three was 1948, the famous renormalization, the thing that Schwinger got his Nobel Prize for, and Feynman also. And there were two ways of doing renormalization. One was Schwinger's approach using equations of quantum field theory. And I can tell you, they're not easy equations. I knew students who were Schwinger students and published a thesis that contained 30 pages of an equation. You know, the math is very, very difficult. I've forgotten it. I couldn't tell you what a field equation looks like today, but that's an example of one. And you do perturbation theory and you expand in powers of the fine structure constant, and you come out with renormalization results. But Feynman came along, and in a strictly ad hoc way, without any derivation of it, he found something that works, an approach that works, involved without any fields, just particles. Particles somehow interchanged each other and interacted with each other. And don't ask me what that Feynman diagram is. I don't know, but I just found it someplace and put it up. So you had this conflict, and guess who won? Feynman. And why did he win? For one reason, everybody could understand him, and nobody could understand Schwinger. And for another reason, the particle approach was a lot easier to use than the complicated equations. I read someplace, I don't believe it, that even Schwinger used Feynman diagrams when no one was looking. But here's the kicker to this. I found this in Frank Wilczek's book, and I encourage everybody to read that book. It's called The Lightness of Being. It's a remarkable book, and he's a field theory advocate. Feynman, it seems, kind of converted. He gave up. As he worked out the mathematics, he found that the fields introduced for convenience were taking on a life of their own. He told Wilczek, this was at a private conversation at some meeting, that he lost confidence in his program of emptying space. And when I think about that, I think, what a part of the tragedy, and I do feel that what's happened is an intellectual tragedy. The fact that the public, and the physicists too, even despite the show of hands I got, I still think that 95% of physicists believe in particles, and there's paradoxes, and we'll come to them in a minute. Despite that, there's confusion all over the place. I'll show you quotes too. And in the meantime, Feynman converted, and never told anybody. If Feynman had spoken up, because he was God, if he had spoken up, anyway, let's go on. Okay. Now I'm going to talk about quantum field theory. And I'm going to tell you how Schwinger presented it. I'm going to start with the pillars, or the basics of the roots of quantum field theory. It did not evolve from quantum mechanics. Schwinger started out with what he called, I think he spent the whole first semester on this, measurement algebra, which takes you, although he didn't call it Hilbert space, it takes you into Hilbert space. And he started with the Stern-Gerlach experiment. And the Stern-Gerlach experiment tells us, much to our surprise, that physical quantities can be discrete, not continuous. In this case, angular momentum. You pass an atom through an inhomogeneous magnet, and this is a field I did my research, my PhD work in, molecular beams. By the way, Cheryl, little memory with you. I was just telling somebody, one of the many moments of regret I have is when I was probably the graduate student, not a postdoc yet, but I had an assistant, an undergraduate assistant, and he said to me, Rodney, can we do the Stern-Gerlach experiment here? Wouldn't it be fun to do that? And of course, intent on the pressure of getting my thesis done, I said, no, we can't waste the time. Boy, do I wish I had said, yes, let's do it. So you come out with the fact that physical properties, quite unexpectedly, can be discrete. You were talking, Wes, you have to accept nature as she is, not as we would like her to be. And discrete, okay, we accept it. We work out the mathematics for that. And he developed this whole measurement algebra, which is really the use of Hilbert space. So the first pillar of quantum field theory is that physical properties can be discrete. And the surprise and the sneaky thing, really, is that Schwinger, went over to describe fields which can be actually continuous as a limit of discrete quantities. So Hilbert space is also used as the algebra, as a relevant algebra for describing everything in quantum field theory. Fields are described by vectors in Hilbert space, which means there can be superpositions and so on. The second principle, of course, is sort of self-explanatory, that there's nothing that compels us to use fields, but we're going to assume that the ultimate basis of reality is fields. Let's try it out, and it works. So the second pillar is we're going to construct a theory of fields. We're going to assume that nature is made of fields. Now you're saying, what is this slide doing here? 30 seconds is all. I just want to mention, I use it in my book to illustrate that color does not exist in nature, if you think about it. Electromagnetic radiation of different frequencies exists in nature. It's only in our brain. Color is imaginary. It only exists in our brain where we put things together. And actually, this slide is not a perfect slide. The lighting is different, so it doesn't quite work here. But if you look at the center cube on the top, I have a pointer here, don't I? That one there. And if you look at the center cube there, you'll say they're different colors. Well, if you look at the proper picture in my book and cover them up, you'll see they're the same. I like that optical illusion so much that I help it included. But the point here is that the second pillar of quantum field theory is fields. And the third one is the principle of relativity. And as I say in the book, the field equations are all relativistically invariant. That was a principle that Schwinger introduced. But there's really two ways of looking at relativity, and this is like this is a resolution that clears up so many paradoxes that I'll come to later. Einstein's approach is a top-down approach. You postulate the principle of relativity, all laws are the same, and physicists work with that. But the field equations are also elegant, and they not only contain the principle of relativity within them, they also provide a physical explanation for effects that are paradoxical if you just look at the top-down approach. And the fourth pillar, although it's not really a pillar, but all theoretical physicists have had the hope that nature is simple. That when we finally, and I can remember many times Schwinger saying things like that, I think he said something to the effect that we should not delude ourselves into thinking that nature is as simple as we would like her to be, but we hope that she's relatively simple. And this is another quote from Frank Wilczek. When you go from a particle description to a field description, we would like the fields to obey simple equations, and they do. All the field equations have this property. Evidently, and I love this last sentence, nature has taken the opportunity to keep things relatively simple by using fields. So, to sum up this section of the talk, and in my book I go through each one of these with a chapter of its own, and I talk about the historical development and the meaning of the fields, and I use this color analogy because, you know, a field I don't know about your experience, but when I took E&M as an undergraduate, I struggled with the concept of a field. And I'm not the only one. It's not an easy concept. Why do they keep the ether for so long? Because it wasn't so easy to picture a field being the entity, the thing that's there, without something to carry it. Well, they abandoned the ether. So you should take a little minute to glance over this. At the time I learned quantum field theory back in the 50s, and even today pretty much, nature is made up of 6 fields. 4 force fields and 2 matter fields. And with a footnote that the strong force field and the baryon matter field are made of more basic but invisible fields called quarks and gluons. And this is a standard model, which came along, by the way. Gell-Mann came to give his talk in the Eightfold Way one of the years that I was there. It was just coming out. Are there any questions about this slide here? Because there's a lot of physics in that slide. I put down there in the last column the color that I arbitrarily associate with each field to help people visualize it. Because like I say, a field is such an abstract concept. But in quantum field theory, that's all there is. Okay. Okay, the next section of the talk, a couple of examples taken from pictures in my book. By the way, my book is definitely written for the layman, as Wes said, but I recommend it to everyone. In fact, if anyone wants to buy a copy afterward, they can at a discount price, too. But it's got a lot of physics in it. You know, I avoid equations, but as the famous physicist said, I can't think of his name, mathematics is just a tool. It's really the concepts that are important, and we should always keep in our mind the concepts. And I don't think the lay people are capable of absorbing the mathematics at all, so I left it out. But the concepts are what's important. So here you see the blue and the green field. The green represents the electromagnetic field, the magnetic field surrounding the Earth. The blue represents the gravitational field. And yes, in quantum field theory, in true quantum field theory, gravity is a force field. It is not curvature, and we'll come to that. It is not curvature in space-time. It's a field the same way electric field, magnetic field, strong force, weak force. And on the right, you see that same picture of an electron field distributed around the nucleus of an atom. Again, don't think that's literally. It's got quite a different shape, but the concept is there. Oh, and also, just to show you, I'm going to mention at the end that I'm not the only person, and it seems I have a room full of people here who have latched onto the field concept, but it's not generally what you read about. And so I've gone out of my way to collect a few quotes from people like Art Hobson and Tony Z, who wrote a textbook called Quantum Field Theory in a Nutshell, and you might want to just read what they've said. An electron is simply an energy increment of a spread-out matter field. Experimentalists choose to call this disturbance in the field a particle of mass m. As Art Hobson said, there are no particles, there are only fields. And it works, and it solves a lot of problems. Okay. Now I'm going to talk about 2 things next. First, I'm going to talk about these paradoxes that I began to be so much bothered by after I retired, and maybe I don't know why, I must have been aware of it before that, but it began to dawn on me that everybody, from Richard Feynman to Albert Einstein, I showed you the Albert Einstein quote, all these 40 years and I still don't know what a photon is. Richard Feynman, you have to leave your common sense behind. Accept nature as she is. Absurd. You know? Joseph Heller, Bill Clinton, I might have his quote here. Before I leave this earth, I want to finally understand physics. Nobody can understand physics. And this is the only way to do it. Okay. I call the three sets of paradoxes Einstein's enigmas. They are special relativity, general relativity, quantum mechanics. And you're going to say, well, Einstein didn't invent quantum mechanics. True. But he sowed the seeds for it with his 1905 paper by painting the photon as a particle. And I call him the grandfather of quantum mechanics, even though he rejected it later. And in each of these enigmas, I'm going to first try to show you that even a few, now physicists like to think we understand everything. We've learned it, we understand it. I guess I probably accepted it too. But a lot of people have had a hard time with these mysteries. In the case of special relativity, there's a bunch of things that just don't make sense. Nothing can go faster than the speed of light. What if you just push it more? Oh, its mass increases. Why does its mass increase? You know, things don't make sense. So first, just read these over, please. I like the last one the best. Joe Bennett was a columnist in New Zealand, and as Wes said, we lived there for a while. He bought an Idiot's Guide to Relativity, from which I learned only that I hadn't yet attained the rank of idiot. I mean, no, it doesn't make sense. How about the Marilyn Vos-Savant? Is she up here? Is there any way for the average person to grasp the theory of relativity? No. Accept the points on faith and then successfully repeat. And she's the smartest person in the whole world. Okay. So in each case, I'm going to show you that people are very, very confused. And I'll show you a summary from my three appendices as to how quantum field theory resolves these enigmas, these Einstein's enigmas. And I remember my insight in this business about time dilation, and I don't remember just when it happened, but when I began to grasp quantum field theory, I said, oh, that explains time dilation. That explains why things slow down. Because in a moving system, the fields that are interacting with each other, communicating from one atom to the next or whatever, must travel a greater distance as what object is moving along. Wow. Objects contract. It's a little harder to see, but it makes sense. Objects contract when moving because motion affects the interaction of fields that holds the object together. This reminds me, I think I'm running very well in time here, so I want to throw this in. In my book, I tell about, what the hell is his name? The Scottish physicist, John Bell. Do you all know of John Bell? Great physicist. I think he died at the age of 35. He liked to propose to his fellow physicists the thought experiment of two rocket ships that take off and are synchronized in such a way that they remain exactly 100 feet apart as they accelerate to the speed, almost the speed of light. And between the two rocket ships is a thread attached from here to here that is exactly 100 feet long. What happens to that thread as the rocket ships, seen from the Earth, keep 100 feet distance between them and accelerate to almost the speed of light? What happens to the thread? Does it break or doesn't it? Anybody want to tackle that question? Anybody raise your hand, want to offer an opinion? The thread breaks. It breaks because of Lorentz contraction. It breaks because of that reason number 2 there. And John Bell found that the best theoretical physicists he knew would not give the right answer, and then he would convince them they would go off and do a calculation as seen from the perspective of the people in the rocket ship or whatever, and they say, oh yeah, it does break. But it follows from Lorentz contraction. Things contract. It's a physical effect, and it makes sense in terms of quantum field theory. Okay. Why can nothing go faster than light? Well, that seems pretty paradoxical, too. If everything is made of fields, and if the field equations that govern the propagation, the evolution of a field, contain a constant c in the time derivative, then the fields cannot go faster than the speed of light. It's built into the way they interact, the way they evolve. And mass increases with speed, because if you have that effect I just talked about, mass means resistance to acceleration. So the mass, which is resistance to acceleration, increases too. Okay. Here with general relativity, two more quotes. I'll pause while you read them to show you that a lot of people, including Einstein's own stepdaughter, and including a very brilliant chemist, Chaim Weizmann. I love that quote. Explained his theory to me every day, and this was in a transatlantic passage when they were coming over the United States. He explained his theory to me every day, and on my arrival, I was fully convinced that he understood it. People don't grasp it. You all probably are comfortable, think you understand curvature of space-time. Most people don't. I don't. I can see it myself in an allegorical sense. You can take mathematics, the same way we can picture not 11 dimensions in my head mathematically, but I can't picture 11 dimensions in space. No, I can't. So I can't picture, and most people can't picture curvature of space-time. And I quote Steven Weinberg in this case to put this paradox to rest. In quantum field theory, there is no curvature. The gravitational field, and I believe, I can't prove it, but I looked it up once. I think Schwinger is the one who actually did the first work on introducing gravity as a spin-2 field. And, let's not go further. Let's just say in quantum field theory, gravity is a field, a spin-2 field. It obeys equations that he derives from sort of first principles, like let's take a spin-2 field. That means it's got a lot of internal properties, more than the others. Let's find a field equation that's relativistically invariant, that's pretty simple, and you come out with Einstein's equations, except there's no curvature. And just to quote from Steven Weinberg, in my view, it is much more useful to regard general relativity as a theory of gravitation whose connection with geometry arises from the empirical properties of gravitation. There's another quote that I didn't put up here where he kind of invokes Occam's razor, simplicity. It makes gravity in step with, in agreement with the other fields of nature. And you think, if you were trying to have a simple universe, why would you have 5 fields that explain everything, and then a sixth field, gravity, that is a horse of a different color? Well, it is in the sense that it's spin-2, but the whole basis of quantum field theory is that there are 6 different fields with different spins, which affects their properties. In fact, that will come up shortly. And finally, quantum mechanics, 3 quotes to show you that a lot of people have had trouble with quantum mechanics. There's a Feynman quote, lose your common sense. Have you all heard that joke? Light is waves on Mondays, Wednesdays, and Fridays. It's particle on Tuesdays, Thursdays, and Saturdays. And on Sundays, we think about it. Talking like all these so-called logical positivists just gives up on it. It's meaningless to ask what reality is. And the answer is, there is no wave-particle duality because there are no particles, only fields. The uncertainty principle, which is so confusing, is just a statement that fields are not localized, they spread out, and there's your Fourier theorem. That even engineers understand. There is no role of the observer. That drives me crazy. I was talking to one of you people here, and well, when you do a measurement, forget measurement. Who can possibly believe, as Einstein said, that the moon exists only when we look at it? I mean, come on, get real. Yet that's what physicists are saying. When you measure something, it changes. Nonsense. Field collapse does occur. We don't have a theory for it. It's part of the gaps. One of the gaps, as I'll show you in a second. Okay, let's move ahead. Finally, I'm going to tell you about the successes of quantum field theory. Oh, and then I have to tell you about the gaps, too. I didn't stumble onto this until I was actually writing the book. I didn't realize this at the time I was a student. But E equals mc squared, which I actually put into the book, although I promised not to do any equations because everybody has heard of E equals mc squared, comes right out of quantum field theory. A high school algebra student can derive it. You look at your field equations. There's a mass term there which governs the evolution of the fields. And you can see, yeah, well, you do have to know partial differential equations, but you can see very quickly that the mass term causes the fields to oscillate with that frequency. And Planck even knew in 1905, his great achievement, that the energy of a quantum is given by his constant times the frequency equals mc squared. And not only does it come out, but it gives a physical basis for understanding it in terms of oscillations of field. Fields oscillate. That was not shown in the picture I showed you. I told you it was a simplified picture. And the oscillations of the field represent the mass and the energy of the field. I mentioned the exclusion principle. One of the great triumphs, and this I think Schwinger played a key role in. I think he was the one who produced the best derivation of the spin statistics theorem that shows you that half-integral spins obey Fermi-Dirac statistics, while integral spins obey Bose-Einstein statistics. So whereas spin zero fields can pile up, Fermi-Dirac fields can't, and that's the Pauli exclusion principle. And here's a quote from Pauli. He didn't get to the elegance of Schwinger's derivation, but he could see that by going to what he calls relativistic wave mechanics, which evolved into quantum field theory, you can derive this. And to jump to more recent times, the Higgs boson. Wherever I look, I'm reading more about the Higgs boson. The irony is that the discovery of the Higgs boson validates the theory of the Higgs mechanism, which is based on a field. The Higgs mechanism works because it's a Higgs field. And the Higgs boson is nothing more than a quantum of that field, just as a photon is a quantum of the electromagnetic field. An electron is a quantum of the lepton field. So I'll give you a moment to read those two quotes from Sean Carroll, who's another strong advocate of field theory. And this is a killer one. I only stumbled onto this. Well, it only came out a couple of years ago, I guess, in one of Wilczek's papers. Wilczek is another one of my heroes, by the way, who is Nobel laureate, of course, who is currently at his level trying to convince people that quantum field theory is the answer. I wonder how many of you know about this. If I hadn't read Wilczek's book, I wouldn't know about it. One of the greatest scientific achievements of all time took place, and nobody knows about it. I don't know how many of you did, but I hadn't heard anything anywhere except in Wilczek's book or Wilczek's paper. they, well, I describe it in more detail in my book, but in a nutshell, they did a huge computer calculation, putting in the field equations for quarks and gluons, and put in certain assumptions to start with, and let things percolate for a while, and it came out with calculated masses of quanta, of fields, that agreed with the observed values. You know, the subatomic zoo, all these new particles that were coming along in the 70s and the 80s, all explained, and even more than that, you don't see the quarks and gluons. The principle of confinement, which seems so weird and desperate, here appears as a footnote to complete and comprehensive reality matching, one of the greatest scientific achievements of all time. I mean, that alone should convince people that field theory is the answer. Okay, Ed Finn. Oh yeah, I do want to read you the dedication I put here in my book. Your dedication. Second, I dedicated to Professor Edward Finn, the godfather of the book, who urged me to write it, gave it its title, now its subtitle, The Theory That Escaped Einstein, and provided invaluable help in finishing it. I could not have finished the book without his help. But most of all, I dedicate this book to the memory of Julian Schwinger, one of the greatest physicists of all time and sadly one of the most forgotten. It was Schwinger who perfected quantum field theory and turned it into the beautiful structure that I have tried to convey to a wider public. So anyway, Ed likes there be gaps. So let me just say very quickly, renormalization is a gap. We do not understand how an electron interacts with its self-generated field. Feynman, and I give him credit for this, thinks there probably isn't any interaction. He thinks the idea is silly. Maybe that's the answer. But it's not covered by quantum field theory. Field collapse bothers a lot of people. Quantum field theory does not describe how or when field collapse occurs, although it can predict probabilities, depending on the components going to Hilbert space. If something collapses into a Hilbert vector, you can see the probability, the amount that vector being in the superposition. And more gaps. Of course, quantum field theory doesn't tell us the whys and wherefores. Why are the masses and interaction strengths of the fields what they are? The field equations are really pretty simple, about as simple as they could be. So that meets Occam's razor, but the particular choice of constants doesn't touch. And then, of course, there's this relatively new discovery of dark matter and dark energy. Frank Wilczek, in the book I mentioned, offers some ideas. And the final one is my favorite, and to me the granddaddy of all mysteries, consciousness, something that happens right under our noses, so to speak. And we don't have the foggiest, we never will probably, although Frank Wilczek thinks that he might. But that's the biggest mystery, we don't touch it. Okay, so that's the gap. Let me conclude by saying to you, and I don't know what to make of the vote that you gave me in the beginning. I didn't expect that at all. But from what I see going on in the physics community, I think there is a trend back to quantum field theory. I mentioned people like Sean Carroll. I have a quote from him. He's giving lectures all over the place, using the Higgs discovery, I think, as a primary hook to pin it on, but telling people that it's all fields. Art Hobson, who's a kind of buddy of mine, he never studied quantum field theory, but his intuition plus the problems that exist with quantum mechanics have led him to believe that, as his title says, there are no particles, there are only fields. People who have written textbooks, Tony Z. I've mentioned, Steven Weinberg is a field man. And I think actually a lot of people, if you look up Higgs boson, you'll find a lot of stuff on the web about the Higgs field. It has to be a field. So I think the tide may be turning, but we have 100 years of momentum against us, where the particle picture has been coming on strong, especially after 1948 and Feynman's diagrams. But I urge you as young physicists, or in some cases maybe not so young, but compared to me, young, to try and pick up this banner. Hopefully, we can eventually convince the physics community and because the people out there, the Bill Clintons, the Joseph Hellers, I have a quote by Joseph Heller, who was trying to understand quantum mechanics and gave up. He concluded the theory is not capable of being understood. To wage a bit of a war, which I'm trying to do, a bit of a battle to try to convince people that quantum field theory is the answer. And if you want to buy my book and be more convinced, I have some extra copies here. Okay, thank you very much for listening. I ended on time, so I'm happy to take any questions you have.
In field theory, are gravitational fields and electromagnetic fields related?
Gravitational fields and
Electromagnetic fields.
well, they're two different. Einstein searched for what he called a unified field theory. His intuition told him, as he carrying simplicity to the utmost, there was just one field. Pauli said to him, Einstein, don't try to put together what God has torn asunder. In quantum field theory, there are 6 different fields. They have different spins, different properties. Okay, there's electroweak unification, so they're very close. But no, electromagnetic field is a horse of a different color from gravity. Gravity is spin 2 for one thing, electromagnetic field is spin 1.
So if a photon is a collapse of an electromagnetic field?
No, the photon is a quantum of the electromagnetic field, which means a photon can be created and travel through space and spread out and be all over space.
So
That's not...
If there's no curvature in wave theory, how does quantum field theory explain gravity affecting the path of the photon?
Okay. I'm not really competent to answer that. I can't give you the kind of answer I think you would want, but it comes out of the equations. It does. There's interaction terms among all the fields. The gravitational field has a property. Gravitational field interacts with everything, with all the... You saw that slide that summarizes the fields. You see the gravitational field interacts with all other fields, and it interacts in a way depending on their energy content.
So I'm not sure that you have completely convinced me with your arguments here. I mean, the way that I see things is that quantum mechanics has some profoundly odd things that happen. And there have been a lot of different proposals put out there, none of them that I think are all that satisfying for how to deal with it. So if you go back to the regular Schrodinger wave equation, you have the collapse of the wave function when you do measurements.
You know how when you say when you do measurements, you know how I feel about that.
Yeah.
Go ahead. I don't like that.
So if I instead look at a particle picture, like Feynman, he would say, everything is a particle, but they're not like billiards. So if I want to determine what the particle is doing as it's moving from point A to B, I have to consider all possible paths and assign an amplitude for each path and add them all together in an appropriate way. And that's how you get interference or the non-local behavior of something that on the front of it looks local, and some people don't like that particular way of interpreting it. I think in the field picture, everything gets hidden in this way that when I'm doing a measurement of a photon, as you were showing, it's collapsing to a point. This very non-local object is collapsing to a point and giving all its energy at one particular place.
For example, in the
which is where in the field theory, this mysteriousness of quantum mechanics that's where it ends up getting put in. We very easily see interference effects and other things like that, because they're fields, of course, they interfere with one another. But because we also see particle natures, it's hard to get the particle nature out of the field, and it's, I guess, postulated as part of the way the field theory is working, that it then looks like a particle in those instances. So I'm not really, it seems like all these different theories are kind of different ways at trying to explain things, but I'm not sure any of them have really fully solved the picture, at least for me.
Okay, no question. For me, I find that quantum field theory doesn't explain everything. There are gaps. I mean, hell, renormalization is a gap. But it explains almost everything that we have observed. It's self-consistent. It doesn't involve any absurdities. But as I say at the end of my book, I say it's your choice. Let me just read you that. I think it's at the very end. Oh, well, this is not what I had in mind, but at the end of Appendix C, is that all there is to it? Did I give too little space to discussing these profound paradoxes? Well, that's really all there is to it. In quantum field theory, everything is fields. They spread out, they collapse, and they do all this without requiring an observer. When I hear people complaining about the paradoxes and inaccessibility of modern physics, I want to ask, what part of quantum field theory don't you understand? It's your choice, you know. But a lot of people, and certainly including me, and I think more and more, are finding out that quantum field theory makes sense. Any other questions?
What is the point of obsessing about different interpretations? Is it particles that behave like fields or waves, or is it fields that have, particle-like properties that collapse into particle-like objects the moment you look at them?
Okay.
It's not going to make you calculate things better. It's not going to make you discover new things. What is the point?
I'll give you my answer, but I also want to read you, if I can find it. I won't find it really in time. I have a quote by Steve Weinberg, who says essentially, physicists don't have time to worry about these philosophical questions. They are too busy calculating. And they make their living by doing these calculations, and a lot of them don't think about it. What is the point of obsessing? Don't be my guy. I just happen to be very interested. In wanting to know what reality is. To me, it makes the difference. To me, I found it a great relief and a breakthrough to understand that if you picture reality as made of fields, it makes sense. So that's what reality is, and to know that it all makes sense. But a lot of people don't care. Steve Hawking says, I don't care about reality. I'll just calculate my things and predict the results of experiments. So it's up to the person. If a person is interested in what nature is made of, it matters. If the person just wants to do his calculations and make his living as a physicist, it doesn't matter.
I just wanted to comment in response to that question about obsessing about interpretations. There's a whole, it's a little book, but there's a fairly new book out, which is all about the so-called transactional interpretation of quantum mechanics. The interpretation was developed in 1986. can't think of the guy's name offhand, but he's at University of Washington. And there's been a couple experiments done that seem to uphold it to some extent. But a whole book, you know, a couple hundred pages on an interpretation of quantum mechanics.
Art Hobson thinks it's very important, I think for the same reason that I do. And he's working very hard to try to convince the physics community that the particle picture is untenable. Frank Wilczek wrote this book to let people know that physics makes sense, that we have a theory that works. That doesn't have any absurdities in it. But again, it's up to each person. Okay. Wes, you have a question?
Okay, you commented about Sean Carroll. Sean Carroll is a general relative, but still, he has a fairly recent book, which is one of the better books around on general relativity. And one of those quotes on his blog, I actually have seen. But he's not a field theorist by background. He's a general relativist.
Yeah, I know. But I only learned about, I'll tell you how I learned about him. Somebody posted a review on Amazon of my book and gave it 5 stars, of course, and said he was led, I forgot to say, he was led to it by having seen a video of Sean Carroll's on YouTube. And that was when I first heard of Sean Carroll. This was within the past year, maybe even 6 months ago. So I'm not too familiar with his work. But he does, whenever he talks, I believe he says, these things are not particles. They're excitations in a field, and we call them a particle. So I said, okay, good for him. He's on our side.
Yeah, as you told me, but as I had seen, he must have about, a couple dozen YouTube videos. They're all, well, some of them are long, but they're worth looking at, worth listening to.
By the way, remember, if any of you doesn't want to be on this video that's being filmed, tell John before you leave to make sure that you're not on it. Okay. Ed, any more questions? Okay, thanks again. I've enjoyed this very much, and I hope that you people of whatever age and education level you're at will believe in this, come to see why this belief is such a good one, and spread the doctrine. Thank you.